today we want to look a little more detail at integration by substitution because it's the anti-chain rule. Chain rule is one of the things that we want to be good at because we're Calc 1 students. Integration by substitution is really something that we're going to want to be good at later on when we are Calc 2 students. But if we're better at the chain rule, we'll be better at integration by substitution. If we're better at integration by substitution, we'll be better at the chain rule. Integration by substitution is just the anti-chain rule. If we find the derivative of a composition of functions, the derivative of f of g of x is f prime of g times g prime. So we take the derivative of the outer function with respect to the inside function, then we multiply by the derivative of the inside function. So if we turn this around, every derivative statement is now an indefinite integral. So the integral of f prime of g of x times g prime of x to x is f of g of x plus c. What we're looking for is a function. When we're integrating by substitution and we want to think about substitution, we're looking for an inside and the derivative of the inside. That's the combination that we're looking for. We're looking for this combination, something that we can call the inside and the derivative of the inside. Specifically, we have a function that's been plugged into another function and the derivative of that inside function as a factor. So it has to be multiplied. If we put a plus there, it's all bets are off. That was not done doing the chain rule. The chain rule says multiply by the derivative of the inside. So we want the derivative of the inside as a factor. So when I say as a factor, I mean it's being multiplied by the derivative of the inside, because that is the hallmark of the chain rule. We just happen to be doing the problems backwards, Jeopardy style. Instead of saying find the derivative of this function with the chain rule, we're trying to look at the function and say the chain rule was used on this. So if we take, let's find some derivatives using the chain rule to see what happens. The derivative of cosine of x cubed, the derivative of cosine of something is minus sine of that thing times the derivative of that thing. The derivative of cosine of x cubed is minus sine of x cubed times the derivative of x cubed, which is 3x squared. So there we are using the chain rule. We're taking derivatives. We're always using the chain rule because the next step would just be the derivative of the inside, which is the derivative of x, which is 1. That's, of course, not how we would write this. We would hate to have the monomial hanging out at the back, so we'll have minus 3x squared sine of x cubed. Just some quick chain rule review stuff. In the next problem, I've got x to the 4th plus 5 all raised to the 1/2 power. We see the square root, we think of that as a 1/2 power because we want to do nx to the n minus 1. So it's a bunch of stuff to the 1/2 power. The derivative of a 1/2 power is to say 1/2 of that stuff to the negative 1/2 times the derivative of that stuff. So the derivative of x to the 4th plus 5 is 1/2 x to the 4th plus 5 to the negative 1/2 times the derivative of x to the 4th plus 5 for x to the 3rd. If we want to clean this up a little bit, I've got a negative exponent and it's a fraction exponent. I've also got a 1/2 and a 4, so we could clean this up a little bit, make it a little more aesthetically pleasing and have a 2x cubed over a square root of x to the 4th plus 5. What we want to notice in the first two examples here is that we have clearly a polynomial inside and a polynomial that's been multiplied by a bunch of stuff, a polynomial factor. And the polynomial factor is 1 degree less than the polynomial inside. In the orange example, I've got a x to the third inside and an x squared on the outside. So that should be, that's a cube to say that x squared is there because it's the derivative of the x cubed. The same thing happens in our square root example. I've got a square root of x to the fourth plus 5. That x to the fourth is inside, and we see that x to the third on the outside as a factor. So we want to view that and see that x to the third is there because it's the derivative of the inside. This is from an integration standpoint. We're thinking of looking at the chain rule, not just how to do the chain rule from function to derivative, but what derivatives were found using the chain rule. So in the third one, it's a little bit different because I don't have polynomials. I've moved the cosine from the function that's on the outside to the function on the inside. So that's the point of this third one. And we have the derivative of natural log of a thing is 1 over that thing times the derivative of that thing. And the derivative of that thing in this case is negative sine x. So I'll have negative sine x over cosine x. I wanted to separate it out as factors to see the derivative of natural log of a thing is 1 over that thing times the derivative of that thing. And I could mash them together in one fraction. And then I could complicate things further from looking at it by writing negative tangent x. But we're going to think of negative tangent x when we go to do this backwards as a sine x over cosine x. This one's a little bit harder to spot, especially in the form of tangent x. But once we see that cosine sitting in the denominator, the derivative of cosine is sine, and that's just right up there in the numerator. That sine is the derivative of the cosine underneath. It's important to note that this is not the other way around. In the tangent x, sine x is a factor in this fraction here. Cosine x is not a factor in this fraction here. The cosine x is in the denominator. I'm not multiplying by cosine x. I'm multiplying by 1 over cosine x. So cosine x is not a factor. It's the denominator. 1 over cosine x is a factor. So if we look at this fraction, negative sine x over cosine x is not a factor of that fraction. Clearly, all I'm going to do is take 3 answers that we just got here and put integrals around them and say, find the indefinite integral of these 3 functions. And it's going to go directly back to what we started with. And we want to point out the things that we want to notice. So if we integrate negative 3x squared sine x cubed, we know this is going to be the cosine of x cubed plus some constant because we're going the other direction, we're integrating. And whenever we're doing an indefinite integral, that's the indefinite part. Some constant of integration, because these processes, the integration and differentiation are not inverses. They're almost inverses. When we're looking at this from an integration standpoint, the first thing that you're going to look for, if you don't recognize what the antiderivative should be right away, the first thing you're going to look for is a substitution. Was this function, was this derivative found with substitution? I see there's an x cubed inside and there's an x squared outside. That's what tells us that we use the chain rule. I see this x cubed is an inside, and this x squared as the derivative of the inside. Specifically, the derivative of the inside as a factor. What we want to note, the other thing that we want to notice is that the important part of the derivative of the inside is the x squared part, not the -3 constant, because that's just a constant factor, and constant factors just tag along when we're taking derivatives. So the important part is the x squared. The x squared is the important part. The negative is just there because the derivative of cosine is negative sine. And the 3 is just there because the derivative of x cubed is 3x squared. What called our attention to doing this problem with substitution is that there's an x cubed inside and an x squared outside. The constants we can sort out. Because if I take this derivative, this antiderivative, if I just divide by -3 all the way through, we'll see that the x squared is the important part. So another version of this problem might just say the integral of x squared sine x cubed to x. So what's missing? We look at the derivative of cosine, or sorry, the derivative of cosine is negative sine, and we don't have the negative. That's okay, because -1 is a constant factor. The derivative of x cubed is 3x squared. We don't have a 3. That's okay. 3 is a constant factor. We have the important part. Here's the inside is the x cubed, and the derivative of the inside is the x squared, the important part of the derivative of the inside. So we're going to be integrating a sine of x cubed and getting a cosine of x cubed. But there should be a -3 because the derivative of cosine is negative sine, so there's a negative. And the derivative of x cubed is 3x squared, so I'm just going to, there must have been a 1/3 that multiplied by the 3 to cancel it out. So the thinking was the derivative of cosine is negative sine. It's not in the integration side, so it shows up on the antiderivative, or it shows up on the integral side. Let's put that backwards. There's no negative. The derivative of cosine is negative sine. It doesn't show up here, so it must show up in our answer. It's only a constant factor, so we're okay. So the derivative of cosine x is negative sine x, and we don't have a negative. So it shows up in our answer. Also, the derivative of the inside, the derivative of x cubed is 3x squared. We don't have a 3 in the integrand, so it shows up, the 1/3 shows up in the answer. So if we take the derivative of negative 1/3 cosine of x cubed, the derivative of cosine of x cubed is negative sine of x cubed. The negatives cancel out. The derivative of x cubed is 3x squared. The 1/3 and the 3 cancel out. We want to point out that we have not talked about the official method for doing integration by substitution, because I'm not going to tell you this semester. You don't get to know. You just have to look. We're taking this as a reading exercise right now. So we won't do any kind of fancy substitutions. We're going to be doing basic substitution, because my goal right now is to get you recognizing when the chain rule has been used. Questions? Well, our other integral was 2x cubed. So we know this already. We found the derivative of the square root of x to the fourth plus 5. It's 1/2 x to the fourth plus 5 to the negative 1/2 times 4x to the third. That ended up with 2x to the third over the square root of x to the fourth plus 5. So we know what the antiderivative is. We know the indefinite integral already. We want to think about what happened if I start changing out some of these coefficients. So what if instead of 2x cubed over the square root of x to the fourth plus 5, what if we had the alternate problem? Oh, well, first of all, let's do the inside outside. X to the fourth plus 5, that's our inside. If we want to do substitution, we have to have the derivative of the inside as a factor. We can be off by a constant factor. So the derivative of the inside is 4x to the third. The derivative of x to the fourth plus 5 is 4x to the third. We look at the top and we see a 2x to the third. That's close enough. We're only off by a constant factor. It's supposed to be a 4x to the third. We got a 2x to the third. So I guess a 1/2 must have showed up somewhere. Questions? So if we look at a different problem, so we know this already. We recognize that with the 2, we're going to have no constants over here. So what if we had some variation of this problem? So instead of 2x to the third, we have just x to the third. Because we already have the problem above, we know that there's going to be a 1/2 factor. So at a certain point, I must have, let's see, this one's been multiplied by 2. If I want to drop that down to a 1, that means I have to multiply everything by 1/2. We want to think about where this 1/2 might have come from. And we got to think about the two things. What happens when we integrate, number one, and what happens with the derivative of the inside. Those are the two places that we could introduce constant factors. So let's think about what those factors are. The derivative of the inside is a 4x to the third. So if there's a 4 that isn't there. So if the inside is x to the fourth plus 5, the derivative of the inside is 4x to the third. So there must be a 1/4 in there somewhere. That 1/4 is to balance out the derivative of the inside. That's getting rid of that 4x to the third. So there's going to be a 1/4 on the other side. The derivative of something to the 1/2 power is going to be a 1/2 stuff to the negative 1/2. Here we have stuff in the negative 1/2. So the derivative of the square root of x is 1/2 x to the negative 1/2. So over here, we're also going to have to multiply by the reciprocal of a 1/2. So we just multiply straight across. 1/4 times 1 times 1 over 4 times a half, or you could put the 1/2 over. I don't know. I'm not sure how you were trained with fractions. I'm not allowed to read your minds to see how you think about fractions. What we're going for is balancing constants. Think about constants from the derivative of the inside. Think about constants that might have shown up when we take the derivative of the outside with respect to the inside. This one's a little trickier because we have to look at the tangent, and there's a lot of stuff that's been kind of absorbed when we write the tangent, because we wrote tangent because we saw sine over cosine. If we write tangent as sine over cosine, we can see that the inside is cosine x and the derivative of the inside is negative sine x. So we have all this stuff like we wanted. Cosine x is the inside. And the derivative of the inside is negative sine x. And I have negative sine x, that's the derivative of the inside. So I'm integrating a 1 over x function, which is the natural log of the absolute value. Natural log of absolute value of cosine x. So it's a little bit different than the previous, because the previous started with natural log of x. And this one starts with tangent. So we started with different domains in each of these problems. And the variation would just be some fraction or some constants. So if we just had the integral of tangent x, we've dropped the negative, so the negative shows up on the integral side. The game here is to recognize when an integral, or when the function that we're trying to integrate was found with substitution. We're trying to integrate a derivative to get back to where we started. And so we're asking ourselves, was the chain rule used in finding this derivative that we're trying to integrate? So our mechanical skill is integration by substitution, but our primary skill that we're working on now is recognizing the chain rule. And the primary idea that we're working on is that integration and differentiation are almost inverses of each other. Any questions? That's everybody okay? It's weird because we treat math like a skill, but because of what we want out of the skill, it's not about just doing the things in math class. It's about understanding what's going on. That's why I care about emphasizing in a semester where I talk about the chain rule. I want to talk about the anti-chain rule because I want to learn things forwards and backwards. That's the important knowledge. Finding derivatives, not really relevant. Finding antiderivatives, not the relevant skill. Understanding the relationship between those two operations, or those two operations, that's the important skill. Does that make sense? It's imagine like if you're learning how to throw a baseball, specifically learning how to throw a curveball. You need to learn the mechanics of that so when you throw the ball curves like it's supposed to. In that scenario, you don't really need to understand the physics of what makes the ball curve. You need to understand the do's and the don'ts of how to throw a curveball. You just need to be able to find the derivative or find the antiderivative. That's what's going to make you effective. But in math class, it's not good enough to just be able to find the derivative or find the antiderivative, because once you're finished with your schooling and you're not in a calculus class anymore, no one's going to ask you to find derivatives and antiderivatives. Those of you working as tutors, offer does not apply. For those of you who have future jobs as teachers, offer does not apply. Plenty of people will be asking you to find derivatives and antiderivatives. Specifically, when you're a tutor, you're going to have to be able to do it. When you become a teacher, you can just avoid it. It's like, well, what did you try? And when the student's like, oh, well, I didn't try anything, I got confused. Like, well, get out of here and come back when you've tried something. Because teachers get to be mean like that. But when you're a tutor, some of you are going to be working as tutors. And if you're not, you should. Pretty good money. And all you have to do is math problems for people. Good job. So those are the kind of like the only situations where you're going to have to find derivatives and antiderivatives. You don't have like those specific jobs. No one's going to ask you. You're not going to be sitting there working on the mission to Mars saying, oh, we need to find some antiderivatives. Then you'd be like, oh, it's a good thing I know. Substitution. I mean, that's just not going to happen. You're going to be like, oh, how many decimal places of accuracy do you need? And then you set the computer to do the job. You know what I mean? How's everybody okay? But because there's all kinds of stuff that comes after this, that's based on not these mechanics so much as based on this kind of thinking, kind of important to understand how the process works. Any questions? How's everybody okay? It's also difficult to give lots of examples because it's so early in your mathematical education. We're still so early in your mathematical education. I know you're thinking, it's like, oh, dude, I've been doing this for 12 years. How could you possibly consider this early in my math education? You're only up to calculus. I know when you're in like 8th grade, it's like, oh, wow, these people are in calculus. But at this point, it's like, you're only up to calculus. Sometimes people will be asking me like, oh, what comes after calculus? I'm like, oh, math comes after calculus because that's when it branches out. Math is just kind of this straight line up the thing of all these things you need to know before you get to start doing kind of like modern math. Hasn't always been this way. For a long time, being good at math was being a human calculator, was being good at the calculations. And so there'll be times like, oh, well, if you want to be good at math, for addition and subtraction, you should probably go to Germany. But if you want to be good at multiplication, you're going to have to go to Italy and get trained there. I mean, but now we've got calculators. And for a long time, I was good at math. I was considered good at math. And I could not approximate calculations in my head for shit. My ability to do mental math and calculate things quickly was pretty bad. Hey Siri, what's the square root of 457? And Siri would be like, is 4 decimal places good enough? And you're like, oh, yeah, that's totally good. You know what I mean? It's not about the calculation, it's about understanding what's going on and the relationship between these operations and what these operations represent. That's why when we're talking about integration, I keep saying shit like integration is multiplication where one of the factors is continuously variable. And I need that to land because later on, next semester, you're going to be spending a lot of time talking about applications of integration. The applications of integration are just applications of multiplication. It might as well be area. Area is equal to length times width. Distance is equal to rate times time. Work is equal to force times distance. Volume is cross-sectional area multiplied by height. It's all just multiplication. Just take one of those factors, make it continuously variable. Now you've got an integration problem. Any questions? Next semester, the hardest problems are going to be about geometry. You won't have problems with the calculus. You're going to have questions about analytic geometry. That's what your questions will be about. How's everybody okay? Everybody looks so very sad. You all look like this. Is it because you thought you were like super far along in your mathematical journey? And I told you you're like barely even started. You're nearing the end of the beginning. So just listen to that first part. You're nearing the end of the beginning. How's everybody okay? I know y'all are aiming to be engineers, so you can stop at Calc 3. Actually, Skyline's less about. Is everybody here? Who here is not engineer? Okay, that's a lot of not engineers. Anybody here math? Anybody a math major? That's good because I had one in the spring, and we only get an allocation of 1 per year. So, like if there was someone who's like, "Oh yeah, I'm a math major," like, "Oh, I'm sorry, I've already had a math major in class. You have to go." Also, it's just too early to be deciding that you're a math major. That'd be weird. I'm always suspicious of math majors that were math majors from the beginning. Because they've been doing problems in their own time. So, oh, I found this interesting math book, and I started working on the problems. All right, so that's integration by substitution. It's the anti-chain rule. You want to look at a function that you're trying to integrate and you're thinking, did we use the chain rule to find this derivative? Because if we did, if I can identify an inside and the derivative of the inside as a factor, then I can just integrate by substitution. I can just anti-chain rule. And if I'm good at the chain rule, integration by substitution would just be like doing that backwards. We've got to be sure that when we're looking for the derivative of the inside, it's as a factor. So let's suppose that we're looking at something that we've seen before. And think, there's a x to the 4th plus 5. It's in a square root. I'm going to 1/2. And this has been done with a 1/2 x, the negative 1/2. So I'm gonna have a square root of x to the fourth plus 5. When you look at, so to make that work, you got to be thinking to make that work, the inside is going to be x to the fourth plus 5, like it was before. If we're looking at this, everything, aha, the inside is x to the fourth plus 5. No one says aha anymore. It's kind of a shame. And you say the inside, the derivative of the inside is a 4x to the third. And you're like, well, aha, there's a 4x to the third. See, I'm saying it extra because no one says it anymore. This would be fine, right? Because there's a 4x to the third as a factor. But if this is a 4x to the third, let's say plus 1, all of a sudden this is not a substitution problem. That just took substitution right off the table because the 4x to the third is not there as a factor. The derivative of the inside is a term, not a factor, and that's not helpful at this stage of the game. Because of that plus 1, the 4x to the third is not included as a factor. It's included as a term. It's one of the terms of the numerator. So substitution is not going to be for us on this problem at this stage of the game. Any questions? How's everybody okay? All right, that's going to do it for today. That's integration by substitution, intro to integration by substitution. It's the anti-chain rule. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.